Hi, I'm Arden Rhoda, and today I want to talk about color. Might sound simple, right? You've got Roy G. Biv in the three primaries, red, yellow, and blue. But what if I told you it was all a lie? A lie built on outdated science and an inability to mix the color purple. Let's start from the basics. There are three primary colors, red, green, and blue. These are the colors that we as humans can see through photoreceptor cones in our eyes. These are called tri-stimulus colors. These colors are separated by their length, as mapped out in an LMS color space, essentially a graph of all the colors you can see from your long red, medium green, and short blue cones. The thing is, though, the LMS color space doesn't account for the full range of colors we can perceive. What do I mean? There's a difference between stimulus and perception. If we could only perceive color in LMS, then the world would look a lot more flat. But that's where our friends, the retinal ganglion cells, come in. The leading theory is that these ganglion cells fill in the blanks when transmitting signals to our brains, causing us to see the in-between colors like yellow. This would make sense given that other animals do in fact have a yellow cone. So basically, you're not seeing yellow, you're perceiving yellow. Not to say those colors don't exist, they do, we just don't have the cones to see them. There are actually a lot of different cones animals can have, like how some bugs can see ultraviolet, they have a cone for that. And the animal with the most photoreceptor cells is the mantis shrimp, with 16 individual cones. I know, it's nuts. Anyway, back to color spaces. Since LMS doesn't compensate for our in-betweens, scientists and colorists have switched to different versions of CIE color spaces. The main one used is the CIE 1976. This encompasses all the hues that we can see. So how does this play into a practical use of color? Well, even though our primaries we can see are red, green, and blue, this only corresponds to light. In physical art, we use their direct complements for mixing, those being cyan, yellow, and magenta. But what about red, yellow, and blue, you ask? Well, red, yellow, and blue primaries have been proved to be outdated for some time now. It's a primary set that is used in ancient times, but for nearly 200 years, we've known that cyan, yellow, and magenta produce a larger range of colors, including the traditional primary colors. But really, the truth is there are no perfect or true primaries. Some sets just are able to make a larger range. But explaining that to a child is difficult, so people stick to the classic. Why is this important? Well, first off, most schools don't ever teach up-to-date color theory. In all my years of education, and as a graduating senior, I was never taught the more correct primaries. I remember distinctly that when I was in kindergarten, I was drawing with colored pencils and scribbled over my magenta with some yellow. When the result was red, I was confused. I thought nothing could mix red. I had broken the natural laws of color, if only I had known. But learning the sciences of color can be really important as it weaves into many careers, not just painters, but graphic designers and photographers need to have a technical understanding of light and color to get their work done. And color science is needed for scientists to find a way to cure color blindness. An understanding of colored light can even be used for mental health treatment, as certain wavelengths of blue light have been shown to help treat seasonal affective disorder. Color science may seem trivial to some, but to many more, me included, we find it endlessly fascinating and important. Also, I want to see what the mantis shrimp sees.
Thank you so much for watching. I really like talking about this topic, and thank you to the Science Ambassador Scholarship for giving me the opportunity to.